Vanillogy, title of Prince's 1997 double disc set, but also a concept in chemistry. Here's an acid chloride and an amine. We've seen this reaction before. Amine's a good nucleophile. I'm going to attack here. I'll get this tetrahedral intermediate, and then I'll end up with an amine, or an amide. If I look at this chloride, this is superficially pretty different than that, but you can almost see it as an acid chloride with this little spacer in between. Right? So now, instead of attacking in a 1-2 sense, now I've got this amine that can attack from a conjugate addition, 1-4 sense. The intermediate looks like this after I lose that acid proton from nitrogen. Just like this thing can break down to kick out a leaving group, so also this thing can kick out a leaving group. What's our product? Our product, again, bears resemblance to this amide, but like stretched out a little bit, right? It's got this spacer in there. And that's kind of what this vanillogy refers to. This could be called a vanillogous amide. It's related to this just by throwing in this spacer at the end. But the chemistry is going to be much the same, right? The chemistry of the amide is kind of driven by the fact that that lone pair is conjugated. This lone pair is also conjugated to that ketone. So it's very similar. So this brings us to one of the most important reactions in medicinal chemistry, in drug making. This is a top 5 drug making reaction. Nucleophilic aromatic substitution. So that's a very fancy way of saying the thing we just said. All right, we're going to have a leaving group that's going to be conjugated to some carbonyl compound. So for instance, here is an advanced intermediate from some drug we want to make. Okay? I've got this nucleophile. So these are going to be potential leaving groups. I know that fluorine isn't a good leaving group usually, but it is in this case, and I'll say why in a few minutes. How can I be able to choose which of these is going to be my better leaving group? Well, it's going to depend on which one I can attack and delocalize the charge into this carbonyl over here. And for that reason, follow the arrows. This is going to go here because I can push those pi electrons up into the oxygen. If I attacked this fluorine, I couldn't do that. Right? There'd be no way for me to get the oxygen, the charge. So after this amine attacks my aromatic ring, again, benzene rings are called aromatic rings, I'm going to get an intermediate that looks like this. Okay, so here, notice I've got 4 bonds to this carbon. The leaving group is still attached. So this is a 2-step reaction. First, I attack, and then in a second step, that's fast, this negative charge will come back down just like it did in the previous. The product we get from this is called afloxacin. So this is an important antibiotic that people put in eye drops, especially eye drops and ear drops. Okay, so I made this new bond. And that really goes to show why this is so important in drug chemistry. In drug chemistry, there are lots of bonds between aromatic rings and stuff like nitrogen and sulfur and oxygen, other electronegative atoms. And so using these as nucleophiles to display something is a really great strategy for making important bonds. I need 2 things to make a nucleophilic aromatic substitution reaction work. 1, I need an electron withdrawing group that's going to be ortho or para to my leaving group. So by electron withdrawing group, I mean some polarized pi bond like a ketone or an ester, nitrile, sulfonyl, SO2 group, or a nitro group, something to hold those electrons. Why do I need that? Again, when it's para and I attack at that position, I can delocalize the charge up to that electronegative atom, and the same goes if it's ortho. But if it's meta, I can't get the charge up that oxygen. It won't work. So that's rule number 1. Rule number 2 is that we need a good leaving group. It turns out the best leaving group for this reaction is a fluoride, atom, or a fluorine atom. Chlorine is okay too. Bromine and iodine actually don't work very well for this reaction. That is backwards from the SN2 reaction, right? SN2, we said iodide was best, bromide second best, chlorine's okay. We never, ever saw fluorine as a leaving group in an SN2 reaction. That just doesn't make any sense. But here, fluorine's a great leaving group. Why? Here's the reaction again. It's important to remember that this is not an SN2 reaction where there's only one step and I'm breaking that CF bond as I'm making a new C nucleophile bond. That's why fluorine is such a bad SN2 leaving group. It's because the CF bond is very strong. So any reaction where you're breaking a CF bond in the transition state, nope, not going to happen. But that's not how this reaction works. Here, the slow step is this first step. It's nucleophilic attack to get here. And only in that second step, when these electrons come down, then fluorine leaves. That step is fast, okay? So fluorine actually makes this reaction faster. Fluorine makes the first step, the slow step, faster because, as you know, it's really electronegative, which makes that carbon really electropositive, right? So the more positive this carbon is, the faster it's going to react with some negatively charged nucleophile or some electron-rich nucleophile anyway. So fluorine, usually a bad leaving group for especially SN2 reactions. But when it's a two-step reaction like this, fluorine is great because it's going to make the addition happen much faster. So we're going to speed up the slow step, the choke point. Then after that, fluorine leaves in a much faster second step. So we need two things for the nucleophilic aromatic substitution. I need an electron withdrawing group, ortho or para, to my leaving group, and I need a good leaving group, preferably fluorine, chlorine, okay. And that's why.